Hi kids, this video is on developing an equation for changing momentum, and the essential question is what relationships determine how much an object's momentum changes? So what variables do impact how much an object's momentum will change? Well, in the last video we talked a lot about sigma F, and which is the unbalanced leftover portion of the forces acting on an object. And sigma F has a mathematical relationship with delta P as well. So would it make sense for that mathematical relationship to be linear or inverse? In other words, when you have more force, more unbalanced force on an object, would you expect its momentum to change by a lot or not by a lot? Hopefully it makes sense to you that the harder you push on an object, the more its momentum is going to be changing. So in other words, there's a linear relationship between sigma F and delta P, because larger forces cause an object's momentum to change more. There's one more variable that can affect an object's change in momentum, and that variable is the amount of time, or delta T, that the force is acting on an object. So picture a car trying to get sped up on a highway to a certain speed. If you just punch that accelerator for a short delta T, how much of an impact will that have on the car's momentum compared to if you hit the accelerator and you keep on pushing on it for a longer period of time? In either case, the car exerts the same amount of force on the road, but in one of those cases, the force is for a short amount of time, and the other case, the force is for a long amount of time. So, would you expect this delta T to have a linear or inverse relationship with delta P? The longer the time, the more its momentum changes, or the longer the time, the less its momentum changes. Hopefully, it's kind of logical to you to realize that this is another linear relationship. So delta T has another linear relationship with delta P, because it would take a longer time to change an object's momentum by a large amount. So we've got two linear relationships. At this point, I'd like you to pause the video and try to come up with an equation for delta P, given those two relationships that we know. Hopefully you did, and you came up with this equation. Delta P equals sigma F times delta T. That shows those two linear relationships. So this equation is actually one of the most important and most widely used equations in physics, and it matters in your life in ways that you probably will come to realize very significantly soon. One specific example that shows the importance of this equation has to do with the difference between a car crash without a seatbelt and without an airbag and a car crash with an airbag, which, as I'm sure you know, is a much safer kind of situation for you to be in. Now, why should there be any difference? Fundamentally, in both of these situations, your body is experiencing the same change in momentum. You're moving along the highway at 60 miles per hour, and then later on you're stopped, right? Your car crashed into something and it stopped. So whether or not you have an airbag or not, you have the same delta P. So if you have the same change in momentum for both of these situations, how come that first situation is so much more dangerous than the second? Well, the reason can be found in this equation. So if we have the delta P, that's the person coming to a stop, but in the first case, the thing that brings the person to a stop is the windshield. And that's a very, very short amount of time to come to a stop, right? Your head crashing into a windshield does not take very much time. And what that means is it's going to exert a whole lot of force on your head for a given change in momentum. So when you have no airbag, because your body comes to a stop so quickly in such a small amount of time, a lot of force is exerted on your body. When you're using an airbag, you have the same amount of change in momentum. Your body's still coming to a stop from a 60-mile-an-hour driving situation, but this time, that airbag allows you to come to a stop over a much larger amount of time, okay? So you have to stop, but you got all that room in the airbag so that the amount of time that your body has to slow down is much, much larger than if you ran into the windshield. And what that means is the amount of force exerted on your body is much, much smaller, which is why this is a much safer scenario than if you don't have an airbag. Another kind of cool example from the news recently, there was a probe sent to Saturn called Cassini, and it flew for 20 years from Earth, and we've been waiting for it to get to Saturn for most of my life. And when that probe actually was launched, right, it started at rest, it started with no velocity, and it actually doesn't have a very strong propulsion system. It only pushes with a force of about 1,000 newtons, which is about as hard as you pushing a heavy box on a rough floor. So imagine yourself pushing that box. How long would it take you to get to Saturn? Well, the thing about this was there's no friction, and when we push with that force for 20 years, okay, if we have a small amount of force for a really large amount of time, it actually allows Cassini to have an incredibly large velocity of 76,000 miles per hour. So this example shows how sort of medium level force coupled with a really long amount of time can allow an object to attain just incredibly high velocities. That's got an enormous amount of momentum because it's going so fast. So we're actually going to change that equation around a little bit. You may have noticed that equation actually doesn't appear in the notebook in your equation sheets anywhere, and that's because there is a slightly more useful format for this equation. Since we know that P is equal to mv, we can rewrite that delta P as m delta v. And the reason we can do that is because when an object's momentum changes, it's due to a change in velocity almost always. Objects' masses aren't changing because of conservation of mass. So change in momentum is the same as mass times a change in velocity. So I'm going to substitute in that new m delta v for the delta P in the equation. I'm just going to replace it because they're equal to each other. So my new equation looks like this. Sigma F delta T equals m delta V. The reason why this new equation is more powerful is because we can actually see how any of those four variables are impacting any other variable. So we have now four variables that are relevant: sigma F, delta T, m, and delta V. And the way it works is that the two sides of the equation have to balance out. So if the F delta T side gets bigger, the M delta V side has to get bigger as well. Or if the M delta V side gets smaller, the F delta T side has to get smaller as well. If one side stays the same, the other side has to stay the same, although it can accomplish that sometimes by one variable getting bigger and the other getting smaller amongst the two variables on the same side of the equation. So for example, if I have an object with a large mass that undergoes a large change in velocity over a very small amount of time, what is that going to mean about the sigma F acting on it? So let's think of an object with a big mass, a bulldozer, undergoing a large change in velocity. So this is a bulldozer, a drag racing bulldozer that's going to speed up as fast as it can. And we're going to say that it does that in half a second. So a bulldozer somehow can go from 0 to 60 in a half a second. How much force would it take? Well, a huge amount of force. And you can also see this mathematically, right? If the two variables on the right are both large, it's going to be a pretty large delta P. The right side of the equation is going to be big. The other side of the equation has to be big too, and if one of those variables is small, the other one must be huge in order to keep that equation balanced. Another example, if I have an object that's got a small amount of force acting on it for a very small amount of time, and this is a medium-sized object, so let's say something like a dog, and the dog pushes on the ground gently, that's why we have a small force, for only a second or two. What do we expect to be true about that dog's velocity? Is it going to change by a lot or not a lot? And the answer is it has a very small change in velocity. So, you know, the two variables on the left side of the equation multiplied together, it's going to be a small sigma F delta T. So the right side's got to be a small m delta V as well. And if one of those variables is medium, the other one has to be tiny to make that side small. To summarize, what relationships determine how much the momentum of an object will change and why? And hopefully you guys, as you move through your days, will start to see examples of objects with changing momentum and think about how the amount of force acting on them and the amount of time that that force acts are the variables that determine how much the object's momentum is changing. Thank you.